Hello everybody! In this video we're going to see examples of how we can answer the two key questions that were introduced in the previous video. So let's start first with a probability estimation question. So remember, with our techniques we're going to be estimating probabilities to be pretty close to the exact value, but we're not going to get the value exactly. So let's start with a function which I'm going to call dice probability. So all I've done is name it. I haven't told you any of the inputs or the outputs. But what I want this function to do is I want to estimate the probability that if I roll 3 dice, at least one of the numbers that shows up is a 5. And these are kind of your typical 6-sided dice. So I have integers 1 through 6 on the faces. So let's make as an input, I'm going to have it to be an integer n. And what this is going to be is the number of trials, the number of experiments. So n is the number of experiments. And as output, I'm going to have a probability. So I'm going to say P for probability. Now what I'm going to do is I'm going to leave space. Eventually I'm going to write something here in line 5, but for now let's say, okay, let's follow the template that was introduced in the previous video. For I equal to 1 to n. So again, this is going to be, we're doing n experiments, so we go first experiment, second experiment, up to n experiments. Then I'm going to say, okay, x, let's let this be equal to a random integer. And remember, 6, I can have 1, 2, 3, 4, 5, or 6 show up on the die. And how many, what dimensions do I want to be returned? So if I were to just do randi of 6, that would just return me a random number. But I want it to be a 1 by 3 row vector. So this is just a vector with 3 elements representing each of the roles, or kind of what shows up on each of the die. So again, you could imagine that the first element of the vector corresponds to the first die, second element corresponds to the second die, and so on. So that's our x value. Then I'm going to say if. Now remember the command any from MATLAB. So what this is going to do, I'll say if any x is equal to 5. So what this is going to do is it's going to say x double equal to 5. That's going to return a 1 by 3 vector that says it's going to put 0 if x is not equal to 5 and 1 if x is equal to 5. So if any x is equal to 5, now remember what we want to do is we want to count this as a success. So I'm going to define our variable s for success to be 0. Then I'm going to say s is equal to s plus 1 in this case, because we have 1 success, so we're going to be increasing it by 1. Great, so then we're going to end the if statement, end the for loop. And now how do we compute the probability? Well, remember, probability is the number of successes divided by the number of trials. So here, P is equal to S over N. And, oh, I forgot to put a semicolon here. So let's test it out. I'm going to save this function. And let's run it a few times. So let's start small. Let's say I do dice probability of just 4. So this is going to do 4 experiments and tell me, okay, what does it think is the probability from those 4 experiments? And here we can say, okay, it's saying 50% of the time. And that might seem natural, but we'll see as we increase the number of experiments, we'll see it's not exactly 50%. Let's try it again with maybe 10 experiments. So here it's gone from 50% to 40%. Let's try it again. Here it says 20%, 80%. So right now what's happening is we're getting a huge amount of variation when we have just 10 experiments, when we have just 4 experiments. So this is our hint that we should try more experiments. So let's try 100 experiments. Now it's saying 43%. Let's try it again. About 45%. If we do it with 100 again, 47%. So kind of the general rule of thumb for these kinds of problems is if you're estimating the probability, so notice that when I did it with kind of small numbers like 10, I was getting wildly different answers every time. Now that I've done it with 100, the first digit has been remaining the same. So here 43%, 45%, 47%. So this first digit is the same, but the second digit is changing a lot. So a good rule of thumb is to pick a large enough number of experiments so that the first two digits are constant throughout the experiments. So now let's try it with, instead of 100, let's try it with 1,000. So here we got 41, about 41%, about 40%, 41.5%. So definitely less variation than even with 100 trials, but still see the first two digits are not staying constant. So let's try it with, instead of 1,000, let's do it 10 to the 4. So 4227, 4179, 4247. So still not enough. Let's try 10 to the 5. 4191, 4237, 4196. So getting closer, but still not quite there. Let's try it with 10 to the 6. So now we're doing a million experiments. Now it's saying 42%. 42%. So we got exactly the same thing again. 4214. But notice now how the numbers are staying, the first two digits, 42, are staying the same throughout our trials. So this is telling us that 10 to the 6 was a good number of experiments for us to try. This is an aside, so don't worry about this for our class, but we could say, okay, what's the actual exact probability? We'll see that it's very close. This is something that we can compute ourselves without too much difficulty. So what this is saying is I roll 3 dice and I want to say what's the probability that at least one of them is 5. Well, that's the same thing as 1 minus the probability that none of them are 5. So 1 minus. Now the dice rolls are independent events. So I have a 5 out of 6 chance that I don't roll a 5. And I do that 3 times, so the power of 3. And we can see here, well, the exact probability is 4213. So we got pretty close with MATLAB. We got 42%, 42%, so it's pretty good. So again, don't worry so much about the exact computation. That was just something that we could easily do here. For a lot of our applications, it's not going to be so simple. But what's the takeaway here is you should try a large enough n so that there's some kind of stability in your outputs. So notice here with a million experiments, there wasn't much variation. Back when we were trying things like 100 or even 10, there was a huge variation. So just something to keep in mind. So that answers the first key question that was brought up in the previous video. What about an example of something where we check expected value? So I'm going to clear the variables and the screen, and let's do something a little bit different. So I'm going to create a new function, and I'm going to call this, let's say, dice exp for expected value. Again, n is going to be my number of experiments, but as an output, I'm going to have an expected value, so I'm going to use the variable e. And what this experiment is going to do is I'm going to say, pretty similar to before, we're going to roll 3 dice and compute the biggest of the rolls. So basically, what's the maximum number that shows up? And what we're going to want to return is what number do I expect to see? So let's do it. Again, I'm going to leave a space because we're going to define a helper variable on line 4. But for now, let's say, okay, for I equal to 1 to n, again, same setup as before, where we're iterating through our experiments. Very similarly, I'm going to say x is rand I. We're still dealing with the 6-sided die, so 6, 1, 3. So same as before. But now what's different is I'm going to say let m be equal to the maximum value of x. So imagine I roll 3 dice and I get 1, 5, and 6. Well, then 6 would be the maximum. And then what we're going to do is, okay, this is where we're going to need our helper variable t. So let's keep our total equal to 0. That's what we're going to initialize it as. And now we're just going to add m to the total. So t is equal to t plus m. So again, expected value, we're taking an average. Just think of it as how you would average any numbers. So we're just going to add up all of the results that we see and then divide by the total. So this is looking good. Let me end the for loop. And now we're going to define our e, is equal to the total divided by the number of trials. So let's save it. and we can run it. So let's say I run dice expected value on, we saw that 10 to the 6 was a pretty good number for this case, and let's see what we get. So about 4.95, and that, think about it kind of in terms of like what do dice look like. This makes sense, right? So we would know that kind of we're taking the maximum of 3 numbers that shows up, and 4.9 seems very reasonable. So I think this is a good place to stop the video. We'll see some more examples in the next one. Thank you for watching, and we'll see you there.